Okay, in this video, we're going to be talking about primary cells, more specifically, the dry/the Leclanché cell. In galvanic cells, this is part 2 to the video that I did before, this is a type of galvanic cell. If you look at this diagram that I have right now, it doesn't look like much, but I can assure you what I'm attempting to draw is a battery. Like your AA batteries, your AAA batteries, your watch batteries, those types of batteries. Those are called dry cells. More specifically, they're called primary cells. We have 3 different types of commercial galvanic cells that we can use. First are primary cells, which is this video. Okay, and the feature of primary cells is that they are non-rechargeable. You are not able to recharge them once you have used all of the components. You just dispose of them after you've used them all. The second is secondary cells. Secondary cells, and the key feature of secondary cells is that they are rechargeable. And the third type of commercial galvanic cell, this goes primary, it goes secondary, hence it goes tertiary. Wrong, it is not tertiary, it is a fuel cell. Okay, and a property of a fuel cell is it hypothetically lasts forever. And I'll tell you what I mean by hypothetically lasts forever in a different video. Okay, so now these are the 3 types. In this video, we're going to be simply focusing on primary non-rechargeable batteries. So if I have a look at this diagram here, what I notice is this is the typical diagram that we have, or typical structure of a battery. It'll always look like a little nib at the top and an outer casing. In this case, the outer casing is made out of zinc. It is made out of zinc metal. It is made of zinc metal, and the zinc in this diagram will act as your anode. The zinc anode. And more specifically, we know in galvanic cells, anode will be the negative polarity of your galvanic cell. So the entire outside lining, the entire casing of your Leclanché cell, or dry cell, I'll write this down so we have the pronunciation, dry cell / the Leclanché cell. Leclanché cell. So the outside casing will be your zinc anode. Then you also have what's known as your cathode paste. And if I were to add to this diagram a few little touches, the first I would add is this little nib at the top is actually a rod. And that rod is made out of graphite. It is a graphite rod. Another way of saying graphite is simply carbon. So this carbon rod, this is a carbon rod, I should have said. And the stuff or the lining that is in between the graphite and the zinc anode is what's known as your cathode paste. So all of this that I have here in my diagram is what's referred to as your cathode paste. Cathode paste. And your cathode paste is what's going to be your positively charged electrode in this case. More specifically, it is actually the graphite that is positively charged. This is the graphite that is positively charged, but your oxidizing agent is actually contained within the cathode paste. So I'll get rid of the polarity here. So that brings the question. I can understand why if zinc is my anode, then your reaction for oxidation, your oxidation equation, can simply be the oxidation of zinc. It is just zinc metal turning into zinc ions. Okay, but what on earth is your reduction equation? Well, your reduction equation is something you have to memorize. It is not actually given on a standard reduction potential, at least in waste. What we have to do, or we have to recognize, is the cathode paste contains manganese oxide. And the reaction looks as follows. It is 2 manganese oxide plus 2 NH4 plus ions, ammonium ions. And it's reduction, so we add 2 electrons because it's gaining them from the zinc casing once it's oxidized. And that forms manganese oxide like this. This is in solid form. Plus ammonia gas. in this case it's not gas, it's aqueous, dissolved, plus water in liquid form. This is your reduction equation. So here's what ends up actually happening. The carbon is a conductor. This is what you can consider as your electrode. What ends up happening is the zinc here and the cathode paste, they are separated. Okay, because they spontaneously react. The E naughts of this entire reaction, I can guarantee you, the E naughts for the entire reaction will be more than 0. Hence, it is spontaneous. So you want to separate your reductants and your oxidants, your reducing agents and your oxidizing agents. So what we end up doing is they are separated here. What happens is the zinc will start oxidizing, as shown by this reaction. The zinc casing will start dissolving essentially into zinc 2 plus ions, and it'll release electrons. The electron flow works as following. The electrons will travel from the zinc casing and into your carbon rod. The electron flow looks like this. Okay, it's a circuit. If you think of it like a battery, the zinc casing will release the electrons and it'll come back into this side of your terminal. That's why when you insert a battery into your TV remote, you have to insert it a certain way. The electrons will leave the zinc casing like this. It'll travel into your TV remote, and you can, or light bulb or radio switch or whatever it is. You end up using that item and that consumes electricity. And the electrons come back into this part of your battery. So the conduction happens like this. It'll go from the zinc casing to the carbon rod. The carbon rod is a conductor of electrons. What happens is the electrons will then go into the cathode paste and it'll start reducing this. It'll start reducing your MnO2 particles. It'll start reducing this and it'll form this reaction here. It'll form Mn2O3. And what we can see here is anode releases the electrons. The cathode paste accepts the electrons through reduction. Reduction oxidation, it is a redox reaction, a spontaneous redox reaction. That's why we have a galvanic cell, which is set up in that way. So this is our cathode, this is our anode. But continuing from here, you'll recognize there's actually one important part that is missing from this diagram. That would be your salt bridge. In this case, the salt bridge is the ammonium ions because it is a weak acid. A weak acid is not as reactive as that of a strong acid, and ammonium in particular is pretty resistant to oxidation and reduction. So inside your cathode paste, you have your ammonia ions. And the ammonium ions, will start turning into ammonia ions. It'll turn into ammonia. And the loss of ammonium to ammonia, that causes a prevention in buildup of charge. It maintains the neutrality of the cell, and it also completes the circuit. And this is how a dry cell will work. So the electrons, to recap, will go from your zinc, the oxidation. It will travel out into the TV remote, light switch, whatever it is, the light bulb, whatever you want, and it will come back through the cathode rod. Graphite rod, sorry. And the graphite rod is the source of where your reduction occurs, and it'll cause the cathode paste inside here to start reducing into this equation here. This is how a dry cell works.